Hello viewers, you're welcome to my channel. Now in this video, we want to look at the remainders theorem. Well, this is a basic case, right? It does not involve arbitrary polynomials and arbitrary divisors. In this particular video, we'll be talking about the one with the linear divisor, the linear factor. Anyway, let's just get into it. Well, when we have a polynomial, suppose that we have a polynomial of in terms of x, let's say of a certain degree, which is actually bigger than 1 or equal to 1, right? So suppose this is a polynomial with remainder r when divided by x minus alpha, then p of that alpha is equal to r. So p of that alpha is equal to the remainder. So this is way too much complex. But don't worry, I'm going to explain this, okay? Maybe I will use some particular examples or just any way that will be fit to you. Okay, great. So here, when we talk about a polynomial, it can be something written in terms of x, all right? Having integral powers, that is having powers that are whole numbers. And then we can divide it by something, okay? Anytime we say a polynomial, let's say 2x squared plus 4x plus 4, right? Let's use this x squared plus 4x plus 4 is divisible by, let's say, x plus 2, right? So this is the polynomial. I can call that p of x. And this right here is a factor. This factor divides this polynomial. So I can call this d of x. That is a divisor, and this is polynomial, the main polynomial itself. That is also a polynomial, but in this case, let's just use p for this one. Okay, so if this is the polynomial, and this right here is a factor, that is, you can split this, all right? You know, if you want to factorize this is a quadratic polynomial. If you want to factorize this, you are going to have x plus 2 times x plus 2. That is going to be x plus 2 all square. Anyway, but when you have p of x like this, all right, it can be written, let me use this example. So this thing here, x squared plus 4x plus 4, can be written as the product of this, x plus 2, all right, with the other part, that is x plus 2 times, now here we are going to call something here, q of x plus r of x. Now, this q of x is a quotient. You know, when you say this divided by this, right? This divided by this, you will have a quotient when you use your long division, right? Your quotient will be here, and your remainder will be somewhere here, right? Then this is a divisor, and this is the dividend. Okay, so this is the main polynomial. You can put it in here, put your divisor here, this one. And when you divide, you have some result here, and you have a remainder down here, all right? Something like that. So what we're going to play around here is that we can actually write this polynomial by saying the polynomial here is the same thing as the divisor times the quotient plus the remainder. Okay, so that leaves us with a very nice equation, which we can rewrite it as p of x is equal to the divisor d of x times the quotient q of x plus the remainder r of x. So all this is a product, right? Now all this I'm writing here, especially this r of x, it may be a constant number. That is, for example, just 3. It's just a constant. So at that point, we assume that the degree here is 0. So it's just r of x is written in terms of x, though it may be independent of x. Okay, so that is it. This is a very nice equation that we'll be using here, all right, to prove this theorem. Great. Now you see that here we are having the divisor here, d of x. Now in the theorem, we have that suppose p of x is a polynomial, all right, and with a remainder r, so that is the remainder, this is a polynomial, then and is the remainder when it is being divided by x minus alpha. So this divisor now is x minus alpha, right? So we have that this is the case. So we don't really care about this other one, this q of x. All we care about is the divisor and this thing. So this is the equation we'll be using over here. Great. So to prove this, I'm going to rewrite that right here. We know that the polynomial p of x is the same thing as d of x times q of x plus r of x. Now notice that this d of x and q of x, the degrees, okay, let's say the product of these two polynomials should be less than or equal to the degree of the main polynomial. Come again. The degree of the product of these two guys should be less than or equal to the degree of the main polynomial. Alright? You know, you can't have this one to be 5, this one can be 7, and this one is now 2. No, it doesn't work like that. So the choice of the polynomial should be such that when you add them up, the powers will add up to the main power. In fact, everything, when you add it with the remainder as well. Okay, great. And now, since we know this, in this theorem, we have that the polynomial, okay, I put it down as p of x, and then we have it to be equal to, in this case, the divisor, when it is divided by, so this is the divisor, we have it to be x minus alpha, right? Okay, great. And then we have this q of x, which has not been mentioned here, so we don't really care about it. So I just put it down here, q of x. And then we have that the remainder, we talked about the remainder, and we called it r, right? Okay, maybe let's just clean up this part of the board and we continue. Okay, so having seen all of this, we want to prove that p of alpha is equal to r. That is, in place of x, okay, you just put alpha. You are going to have r as the result. So let's just do it over here. So since we've gotten this, all we need to do is to go ahead and substitute alpha in place of x. This is very, very nice, alright? Okay, so you go ahead and substitute alpha in place of x, so you are going to have, let me just put it down here, since this should just be the last step. So in place of x, you put alpha. That means that when x is equal to alpha, so in place of x, you just put alpha like that, alright? Okay, great. So this will be equal to, in place of x, you know, since we are doing it to the left-hand side, we also do the same to the right-hand side, alright? So in place of x over here, we are going to have alpha, right? And we subtract alpha from it. That is alpha minus alpha. Of course, you can see where we are heading. Okay, so this is times q of x outside, and then we add it with r, alright? So, you observe that alpha minus alpha is 0. They are the same thing, irrespective of the different color in the ink I'm using, alright? They are the same. So, alpha minus alpha is going to be 0. So, 0 times q of x. In fact, everything there runs down to 0. And the only thing we have left is this r. And on the left-hand side, we can put it down as, p of alpha. So, we have p of alpha is equal to 0 plus r, which is just r, alright? And this is what we have over here, and that ends the proof. So maybe I can just do this and go ahead and shut the box. Okay, very nice. Well, I would like to use this and solve some past questions for you guys. Okay, some examples, actually, little tasking ones, but don't worry. If you can understand this and understand this equation right here, in fact, you are done. So let's just go ahead and solve some examples in our next video. Okay, thanks for watching.